Okay, collapse of the wave function. According to Roger Penrose, you can see here I've drawn a light cone due to special relativity, and all I've done is graph gamma here, and I've graphed phase velocity here. Gamma is 1 over L, and a phase velocity is just x times y. Y equals x, and then gamma is just the square root of 1 plus x squared. So that's how I get that parabola shape, and that's normally how you see it graphed the special relativity. So that's usually called time dilation, and that's usually called the speed of light, and this one's not moving at all, and then sort of as you move faster and faster, time dilates. Okay, so that's normally how it is, but mine's not distorted. Okay, so let's say a particle is created here, and then it heads off and into a particle detector, and then using Roger Penrose's example of a spin half particle, he said that Alice measured in this direction, or the particle was measured in this direction, and it wasn't that way, so the particle collapsed this way. Okay, and what that means is that there's a quantum reality where momentum is conserved, and there's nothing fishy about that, but the fishy bit is that conserved momentum seems to go backwards in time, then come back out and head over to Bob's particle detector, get into Bob's particle detector, and then using Penrose's example, Bob measures up, and in other words he measures it here. So inside the circle is quantum reality, and outside the circle is classical reality, classical reality, and this is this interface. So he measures this way, and it's yes, and it's a yes. So that means momentum must be conserved, and that goes all the way back to backwards in time. So it's this way. And now let's just draw it a bit bigger. She measured that way, and the quantum reality from Bob that was already there, had come backwards in time, was here. So we're looking at the probability of this one collapsing to there, and we use this angle. So that was a yes, that's what happened. And for Bob, he measured up, yes, and somehow momentum was transferred backwards in time from Alice's measurement, and it's going to turn out, this is the thing that Roger was sort of staring into space thinking, oh yeah, the probabilities are the same. In other words, the probability, the angle for Alice is the same as the angle for Bob, so he knew that somehow these are always the same. And then he started questioning free will. But anyway, normally what they do is they just have a single wave function. So let's just draw it up here, and then they'll just put the Alice's collapse here. I'll call it Alice's classical reduction, and then Alice's quantum reduction. This is the one that somehow instantaneously goes into Bob's detector, and then Bob measures this way successfully, and it seems to depend on the probability, which depends on where this quantum reality is, Alice's quantum reality is. So this is Bob's classical reduction, and somehow his momentum is conserved back into Alice's detector, and so it ends up that they both have the same probability of success, and that's why it actually ends up 50% after heaps and heaps of trials. It finds you get the 50% result, because the probability is the same, always the same. In other words, no matter where you go round on this, wherever you make a measurements on this detector, in the end there's a 50% probability. I didn't explain that anyway. So looking at the relativistic slide rule here, let's rotate Alice's one so that it's just pointing up, and if I do that, then here's the angle here, here's Bob's quantum reduction, and that's Alice's classical reduction. And let's take Bob's classical reduction and let's rotate this around so that it's pointing that way. And again, how do you calculate the probability? Well, because it's spin half particles, we actually want these angles in here, and by geometry you find that these angles are half the spin half angles. That's just geometry, basic geometry, which is a fact. So then what you do is you take the cosine of that, of these angles, and because you've got a right angles here, the cosine is actually that one, and then you just square it, and that gives you, and I'm going to draw it in, gives you this length here. So this is the probability of Alice's particle collapsing, and the relativistic slide rule says that that's L, and that's L squared. So you've squared that, and it's equaled L squared. So that's the probability of collapse. In other words, this is L is amplitude of all, and when you square the amplitude you get the probability of collapse. Okay, and so this is Bob's quantum reality that somehow got into here, and according to Roger Penrose, their lines of simultaneity cross. In other words, it goes backwards along the light cone, so that it actually happened before. In both cases, the quantum reality has happened before the classical reality. So you might remember I was talking about frequency increasing as you fall into a gravitational well, which means that the clock has gone ahead in time, which means that it's actually it's already happened. Things that haven't happened in the classical reality have already happened in this lower gravitational well, lower down in the well for the clock that's fallen into the gravitational well. Frequency has increased. Anyway, let's draw that one in, and that's the probability that went back that way into here, again, you're just doing trig. You're taking cosine of that squared and you're getting L squared, and you can see in this case the distance is 0.75, which means it's 75% probability for both of them. So both of them have a 75% probability of being successful in this case. And as I was saying up here, normally they just have a single, they say that there's a single wave function until collapse. Oops. And what are these? What is that distance? And that distance, well, it's actually L over T, isn't it? It's actually this distance and this distance, which once the collapse has happened, they're actually in different directions, but within the detector it's all heading the same direction. These will always be heading the same direction, no matter where they Bob and Alice randomly make their measurement. You'll find that say the measurement's made there by Alice and say the measurement's made there by Bob, you'll find that these will always be parallel. So there is, in quantum realm, there's only one direction, line of simultaneity. But during the collapse, it seems that you have to sacrifice that in order to get a single timeline, which is the constant in this case. So time's heading that way, heading up for Alice and heading down for Bob, but this is just a reflected, so it's heading in the same direction for both of them. Yeah, and it's gonna collapse to get together, and the other, so this distance is L. So I was saying, yeah, that's Alice's measurement and conservation of momentum. Here's Bob's measurement, conservation of momentum, and you find that that distance is always L, and that the probability of collapse, you just square it, square L. Or from a trig point of view, it's just cos times the angle there, halved, because you want to find that, and you square it and you get the probability of collapse. Alright, clear as mud.